This video is both a review with a little tutorial information thrown in. Before I start on the review, I'd like to mention a few applications for a variable isolated AC power supply. Obviously, it can be used for making a YouTube video in 24-volt AC industrial control applications, maybe to determine the input voltage, current, and power specifications and requirements. It's great for designing equipment. In fact, it can be used to simulate a power transformer. The unit I'm reviewing has a simple leakage testing feature for safety. In troubleshooting, it can be a great tool for diagnosing and repairing defective equipment, as bolted in the second column on this slide. In this video, I'll be reviewing the B&K Precision Model 1565A. This is an isolated variable AC power supply. Adjustable output voltage is 0 to 150 volts AC. 3 amps continuous output, 4 amps intermittent with the rest cycle. Displays voltage or current readings, but not simultaneously. It has an isolated transformer to eliminate or hopefully reduce a shock hazard while servicing hot chassis equipment. Has a built-in soldering iron temperature control rated up to about 100 watts. It has an expanded leakage current scale, circuit breaker and fuses for overload protection. And when I was making this video, checking the internet, I saw prices somewhere around $400 to $500 US dollars. I think it lists closer to $600. Another unit that's very similar to it is the Syncor PR57 AC power supply, and you can usually find it used on eBay. And I could be wrong, but I don't think Syncor is still in business. And if someone knows for sure, please leave a comment below. I will be using PowerPoint slides that I've created in a few sections of this video. And for your convenience, the slides in a PDF format are available on my site, tigermultimedia.com, under the navigational link you can see right here, Reviews. And first I'd like to lay a little groundwork. Get it? Groundwork? Several standards define schematic ground symbols as follows. You have an earth ground, common ground, and a chassis ground. And it should be noted that I've seen a lot of published schematic diagrams, and they tend to mix these first two, the earth ground and the common ground. Earth ground is just that. It's a reference point and an electrical connection to the earth. And here's a look at my ground rod for my lab that I showed in my tour video. And then there's a common or signal ground. And there you can see I've kind of got a circuit there. It's an audio amplifier I made over 30 years ago. And please be kind. I did the PC board artwork with tape. And in this area you can see large areas of metal for common signal and power supply grounding. And it allows for return paths for the signal and power supplies. And the next one we have the chassis ground, and it's referenced connected to the conductive framework or case of the device. And this can provide more efficient connections or for adding, say, a level of safety to the device. There are two pictures shown in this slide, and it's the inside and the back panel of a homemade electronic DC load I put together a couple of years ago. And in the upper right-hand corner, the white arrow is pointing to a chassis ground connection, while the other picture shows a white arrow pointing to an AC earth ground connecting to the chassis ground. Since this video is a review of an AC power supply, and I'm located in North America, I'm showing typical AC outlets and some AC power cords. The outlet sockets have 3 connections. The large blade slot that you see there on the right is the neutral, and color of the wire is usually white. The small blade slot is the hot, with the colored wire usually of black. And the last pin is the ground connection, and a colored connection wire of usually green or a bare copper wire. And in the picture to the right there, we have plug 1 is a non-polarized 2-prong connector. And in the picture I took, it might be kind of hard to tell that the blades are the same size, so that particular plug could be inserted into the socket either way. Plug 2 next to it shows a polarized plug with one blade larger than the other. so the plug can only be connected one way to the socket. And plug 3 is a 3-prong plug, and again can only be plugged into the socket one way. And the NEMA reference designators for the plugs and receptacles are shown in the picture. My utility power company is Pacific Gas and Electric, and they reference a standard nominal voltage of 120 volts plus or minus 5% at the service panel. And you can do an internet search on a thing called boundary tolerance voltages and read the PG&E document on the subject, which has a lot more detail. Note that at the top of the slide I listed several common US AC voltages. And the analog meter is the one that's on my AC supply that we're going to be showing in a few minutes and reviewing. And note on the top scale that it has the set, VA, and leakage reference is 120 volts AC. And more on that reference and those other voltages later. I reviewed several isolated variable AC power supplies. And from the information, I made a simplified diagram of a typical supply. So let's take a look at the diagram. And starting over here on the left-hand corner, you can see we have a power plug that is also connected to the chassis, and that pin also ends up at earth ground. We have CB1, which is a circuit breaker, I think rated about 3.5 amps. We'll talk about that in a little bit. Then there's a power on-off switch, SW1, and then it goes to some sort of an indicator, and that's I1, which is in shunt with an auto transformer T1. And then you can make the voltage at that node coming off the wiper adjustable. And then it goes through a fuse. And the fuse is actually in there because at lower voltages it may not trip the circuit breaker. So this is again is protection for the transformers. And then over T2 performs the isolation. And if you notice, it's directly connected to the hot and then down over here to the neutral of the outlet socket. And you can see that this socket is a 3-prong, so it's got a chassis ground connected to it. And a third section, kind of in the simplified diagram, there may be some form of metering so that you can measure voltages and currents. Here's a picture and schematic diagram of a variable auto transformer, also known under the trademark Variac, which I think was from General Radio. In the schematic diagram, you can see that the line voltage of 120 volts AC is applied to a section of the transformer's winding at nodes A and C, with A being set up as a reference. Node D and node C define a portion of the transformer's winding, which by induction allows the auto transformer to step up the voltage. So we have 140 volts from our reference node A to node D. Node B is the output and wiper connection and can continuously vary the output voltage from 0 at node A to 140 volts at node D. Some auto transformers or isolation transformers are tapped, and then they provide a fixed stepped voltages. The wiper is usually a carbon brush that is designed to minimize the currents flowing in the shorted turns of the windings, which is caused by the brush contact. In the picture, you can see that the brush is riding over the magnetic wire of the coils, and the contact area has the insulation removed from the wire. Please note that we have only one coil in the auto transformer, and therefore no galvanic isolation, and therefore, of course, we're going to need another transformer. Here again, we have a diagram of and a picture, and this picture I took from my AC supply. And most transformers with their primary and secondary windings can perform the isolation function, but not all isolation transformers have a 1-to-1 turns ratio, which is just the ratio of the number of turns of the primary and the secondary windings. In fact, many of the supplies that are variable or tapped do not have this ratio. As you can see in this diagram, this transformer has a 1 to 1.1 turns ratio. So this transformer is performing isolation and also stepping up the voltage from 140 volts AC to approximately 154 volts AC. Obviously, there's losses and so on and so forth. Auto transformers are available in many different ratings, but a very common one is for 120 volt systems is having 140 volt output. Therefore, having the auto transformer before the isolation transformer, when I showed you in that simplified diagram earlier, allows the isolation transformer to output an even higher voltage of around, say, 150 volts. Okay, enough groundwork for now. Obviously, you kind of want to look at the actual unit. Just before we start, here's also a shot of my AC power supply. I built it about 30 years ago. Some of it's starting to rust there a little bit. And it's good up to 150 volts. And I built out just spare parts I had laying around. So you can see, because of the big variac inside, I couldn't really put the isolation transformer inside. So I bolted it on the outside of the unit. And I think that's a feature. That's my special expensive air cooling modification. But it still works. It's very bulky, heavy, and I did like to have the currents and some extra fancy features, and that's kind of why I went with the B&K unit. Okay, and here we're taking a look at the B&K Precision AC power supply. It's the model 1655A. Zoom a little closer here on the front panel. You have two isolated receptacles over on this side, and I'll talk about those in a little bit. This is the control, which runs a variac that regulates the voltage from 0 up to 150 volts. This dial, probably never really used this myself, but this is a triac driven output on the back, and it's for plugging in a soldering iron, and therefore you can control the temperature. And it's pretty much independent of the power supply. It has its own fuse, has its own power on-off switch. It runs from 70 approximately to 100% for putting the power out. And therefore, when you turn it down really low, they're saying that you can have your iron idling. And then when you want to take it up quickly to temperature, it's pretty much ready to go. Again, not a feature I'd use. Has a actual mechanical power on-off switch, indicator light. These are LED little NE2 lights up here, kind of old school. Over here you have a nice analog meter. I like this, and it's a 3 1/4 inch meter. Pretty clear scales there and everything, looks pretty nice. And then you have a selector switch for your metering. So you can choose 0 to 150 volts. You push this in. Oops, sorry. Press it in like that. You have two amp ranges. You have 0 to 4 amps, 0 to 2 amps. And then you have leakage testing between common or between hot. And again, I'll explain these later and give a demonstration. And it does have a mechanical 0, but it looks pretty good. Again, the camera might not be showing it quite right, but because of parallax and stuff, but it looks pretty decent. The case seems to be steel construction. The finish looks really nice. It is heavy. It's about 22 pounds. So if you're considering putting it up on your workbench or something on a shelf, you might want to consider that. And then in the back, we have a circuit breaker, a little over 3 amp circuit breaker. We have a special fuse that protects the transformers. And then there's another fuse inside for the soldering iron. Here's where our input comes in. And it's kind of schizophrenic. It says set it to 110 volts AC, and up here they say, set it for 120 volts. And you also see some 115 volts mentioned in the manual. So something we need to kind of talk about. I'll try to help clear that up and explain it a little bit. Okay, kind of a brief explanation, sort of an explanation, because it is a difficult topic. Which reference voltage, for that matter, which procedures? As a hobbyist or troubleshooter to determine what voltage references you should use, I would recommend try checking an information label on the unit, specification tables in the owner's or service manual, and which standards. And that will then dictate, of course, the procedures you should follow. For example, at the bottom of this slide, leakage test would require the standards organization, if it is a Class 1 or Class 2 device, which, believe it or not, a human electrical equivalent model you would use. And this is why you might have an AC motor specified at a terminal voltage of, say, 115 volts plus or minus 10% with a frequency tolerance of, and I think you get the idea. And then over here is the receptacle for the soldering iron, rated up to approximately 100 watts. Again, something I'm not going to use it. Like I said, it is triac driven, so it's chopping up the sine wave, which you don't want, of course, for your regular power supply. And that's why we're using an auto transformer in a system like this. And then this is a leakage current probe right here. And again, we'll be demonstrating this and talking about it in just a couple of minutes so that you can do some safety testing and checking. So overall, I like it. It seems to be a very clean design. I do like analog meters, although you're not going to get a high degree of accuracy or resolution from this as opposed to a digital meter. But again, an AC power supply like this, when a lot of its applications, this is more than adequate. Most of the percent tolerances and accuracies, it's plus or minus 5% on the voltage scale, but it's for full scale deflection. And then it's plus or minus 5% for both the 2 amp and 4 amp current ranges. There are calibration pots on the inside we'll take a look at when we take it apart. And there's also calibration for the leakage current. And here we have a little close-up look at the 3¼ inch analog meter. The top scale right there, we have 0 to 150 volts. From 130 to 150 is in red because that's a D rating for the unit. There's also a set 120 in green. We'll talk about that in just a second. The second scale below that, 0 to 4 amps, and again determined by the mode selector switch. The unit supplies 3 amps continuous. Then there's again a derating from 3 amps to 4 amps. You have a particular duty cycle, say for example on for 4 minutes, off for 5, or rest for 5 at a lower current. And then you also have a scale down here, 0 to 2 amps, and again set by the selector switches below. So it gives you some little bit better different resolutions. And then if you do have it set to the 120 volts, what they did was they took just simply mathematically and just silk screened on the green scales. And these are the volt amp scales, assuming you're at 120 volts. And so this doesn't measure real power or anything, doesn't deal with the power factor. In fact, all it's doing is measuring the current and knowing that if you set it to 120, then you can read the VA directly from there. And it can be convenient. And again, you would have the 2 scales for the 0 to 2 amps and the 0 to 4 amps. Then the very bottom scale is the microamp scale. And you have 0 to 5 milliamps. It's a nonlinear compressed scale. So it expands down here in the lower area for sensitivity, then compresses up at the higher one. And the areas normally you're interested in is maybe 0 to 500 microamps. Some safety specifies at 750 microamps or 1 milliamp, but quite a few standards go to, you should have leakage currents less than 500 microamps. So that shows it, and that works with the leakage probe. And again, we'll talk about this a little bit later. Okay, what we'd like to take a look at now is the leakage current probe right here. It is Cat 3 rated. It has a shroud over the point here for protection, and it's interlocked. You can't move the shroud back until you've pressed this button right here. It pushes in, as you can see right there. I'll zoom in just so you can get a little closer look at that. So right here with my thumb, I'm just pressing this down. When you do press it down, if I come into here, you can see that this plastic retracts. A little hard to see there. You can see it's going back and forth. And so when you come up to make a connection, you simply press this down, and then it will push against this and expose the metal tip. So additional safety. There's also, you get a mystery component in this unit. There's a turn right here, and you can actually unscrew the probe tip. And then you get this part in here, it slides out, and it definitely looks like just an inline fuse, but it's completely unmarked, and it's not mentioned at all in the operator's manual. And maybe again for some protection or something. I know the resistance going into the tester is quite high, and so a few tenths of an ohm wouldn't make any difference if you had a fast acting or fuse in here maybe for additional protection. So I think they really should have included some sort of information about this in the manual. And I'm going to maybe show an example of making some leakage measurements. And you have a choice with these 2 selector switches between your common or your hot to measure the leakage. Remember, it was the bottom scale. And I'll zoom in just a second to show that. Up here again is that electronic DC load I built. And when I showed in the tour, I indicated this has just got contact paper on it. So all these marks and everything don't count. And this probably look crooked, and you see everything's loose. There's actually 4 screws that go into it. And so everything's loose on here because I want to take it all off, pull the paper back off, and then put on a custom faceplate. So let's see if I designed it correctly, if we pass the leakage test. So here's our plug. I'm going to plug it into one of the sockets. Turn the power supply on. And then I'm going to select measure between the common and the hot down here. And because this chassis up here, if I wired it correctly, should be grounded and everything, and this is comparing to the common neutral, there shouldn't really be any leakage current. And again, you have to measure at a particular voltage. And they recommend in the manual, they say 115 volts, and yet they have a calibration over here at 120. And it really depends on the specification for your standard that you're making the measurement with. So I'm going to go ahead and I'm going to set it for 120 volts. So I've set the meter to 120 volts, put it to measure between the common. Go up here, I have to press this button in. I'm going to press this and then push against it. And you can probably see that when I do this, there is absolutely no current that is at least detected on that meter. So now let's see if there's some leakage between the hot and this connection. And generally, under most standards, you need to be below 500 microamps. So I'm going to just repeat this process of pushing into here, but so that you can actually see it, I'm going to go ahead and zoom in on the meter face. Okay, so go ahead and I'm going to make the connection. It's just off camera there a little bit. And you can probably see that it just raises up slightly, well below 100 microamps. So this would be classified as an acceptable leakage current. Again, want to keep it below the 500 microamp range. So one of the things we could test is, since we have a variable AC power supply, we can vary the voltage maybe and run particular specifications on this thing, how well it performs. So maybe I'd like to find the dropout voltage of where this thing goes out of operation. So I've plugged it in here. We know that we have it set for 120 volts. And then again, if it has to be a different voltage, you would check maybe on the back panel of the unit or service manual or operator's manual, and they may spec 110, 115. Again, I've designed it for 120 volts. And then we can turn the unit on. And it takes a minute, a few seconds for it to warm up, but it's set for the DC load to handle 7.46 amps. And this is a 10-turn pot, so you can dial in kind of whatever you want. So, you know, if you want to set it for 5 amps or something like that, you can bring it down. Again, I'm not going to do this really quickly, but oh wow. Okay, 5 amps that you could set there. Again, I don't know if you can see that or not. And this indicates that the unit is powered on. And so what I could do is I could be looking at this, and then I could increase or decrease the voltage to see how it works, you know, over a particular voltage input range. Really cautious when you take the voltage up, be sure you know what the limitations of the device are, so of course you don't damage it. Here I'm going to do a dropout test, so I'm just going to turn it down. I'm going to look at that 5. And again, not sure you can see that or not, but I'll tell you when it goes out. So I'm turning this down right here. And there you can see it's dropped out, went kind of quickly. The fan went down. You may not be able to hear that either. I'm going to turn it back up, and there's my 5 again. If I turn it back down, it drops out again. I can kind of find the point that occurs at. And so I could note that, and it's at about, 97 volts or something like that. So it starts going out of specification at 97 volts. And then I could mark that. And by turning it up past the 120, you might find out where a specification changes. But again, very cautious. You don't want to exceed the ratings of the unit. And then the other thing is, when you flip this over, it electronically switches this output on. And since there's nothing hooked up to it, there's an electrolytic there, it shows 0 current. But if there was a particular device that you're testing, it would show the current. So that's your set current. And then that would be your actual current. And it has also thermal protection circuitry in it. So hopefully sometime I'll tear this apart and kind of explain how I built it. It's all analog. There's no microprocessors in that particular one. Another thing we could check is the output voltage and sort of the accuracy of the analog meter. So I have 2 probes here. I do have the unit turned off again, kind of for safety. These are in parallel. The book doesn't directly mention it, and the labeling up here is a little confusing. It says 3 amps continuous and 4 amps intermittent. It sounds like they might be slightly different, but they're the same. So just for separating things, I'll put this in the common. I'll put this over in the hot of the other one because it's effectively putting it into that particular lead. Just makes it a little easier for connection. Power the unit up, being careful not to touch those. And then we can read the voltage. And I'm going to set it, again, there's a parallax error here and everything, but I'm going to set it for about 120 volts. And you can see it's reading very nicely. But I have to be honest, I did calibrate this unit earlier. And it was within specifications, but it was off just a little bit. And just very easy to tweak it and to set it. And then again, I don't know about linearity and stuff, we could check at different voltages. So if I went down to half of that, say at around approximately 60 volts, seems to be pretty reasonable, 60.6. And again, I don't have it set probably exactly right. So I'm very happy with that in terms of the accuracy of the analog meter. Okay, another thing we could test is the ammeter and the current capability. And here I built a little dummy load and have a bulb here. This is a service rated bulb, so it's rated up to continuous operation at 130 volts. That's a 150 watt light bulb. And then this is a polarized plug, so I broke the connection in here on the hot side so that I could insert an ammeter in series with the load. And I set it at 3/4 inch spacing, so you could have a shorting plug or something like that, plug in there if you just want to, maybe check for voltages or just drive the load. And then another very important thing is you have to make sure you colorize the 5-way binding posts to match the box. So I'll go ahead and stop it just for a second and go ahead and make the connections. Okay, I've made the connections, and so I'm going to put it on the 2 amp scale, and I'm just going to adjust this up until this reads 1 ampere and then compare it to the meter. So just go ahead and turn this up. And there's approximately 1 amp, and then I'll go ahead and zoom in on the meter so you can just take a look at it. And the camera's offset, so we've got a bit of parallax there, but you can see it's at 1 amp, and it's actually, if you perpendicular the scale, it's right over 1 amp. And I cheated a bit because I did calibrate it. And I was interested in the 1 ampere range because I'm going to do some projects around those currents. And of course you could set it, they recommend setting it at the 2 amp and the 4 amp, making comparisons. So looks real good. And of course another thing is you basically have a dimmer. Ooh. One nice thing is though you are varying a sinusoidal wave and you're not chopping it up. Okay, I do an additional test here for higher current. I have a shop vacuum cleaner, and what I'm going to do is I'm going to mute the audio just so you have to listen to the fan. It's just right below, and I've plugged it in over here. So I just want to turn it up to 3 amps and see how it's doing. Let's take a look at how an isolation transformer might be helpful in testing devices. In the battery-powered unit shown in the lower portion of the slide, there is no earth neutral reference, so the connection of earth reference test equipment is usually not a problem. However, you normally still cannot separate test leads that are bonded to the same reference. Therefore, in this video, I'll be spending most of my time on the AC mains powered devices. Looking at the circuit above, we have a schematic diagram of a simple half-wave rectified Zener diode regulated power supply. The important thing to note is that the unit has a step-down transformer T1. Also, the unit uses a 2-prong non-polarized AC plug. You can see in the diagram that T1 provides for a galvanic isolation between the line voltage circuits and the rectifier and regulation components. Therefore, the neutral and earth grounds are not directly connected to the same common ground. There are 2 main areas to consider when testing the device. 1, that the DUT and the test equipment will not be damaged, and 2, more importantly, that the person making the tests will not be damaged. Looking at the first area, a common problem is when the test equipment has an earth and chassis ground which may be bonded together. A common, very powerful test instrument, and definitely one of my favorites, is the DC coupled oscilloscope. Most bench scopes have an input reference lead, shown here terminated in an alligator clip, connected to the earth ground. I checked one of my scopes, and the input at the BNC connector shows 1 megohm shunted by 16 picofarads with a maximum input voltage of 300 volts. Note that the scope's chassis, earth, and common grounds may be connected together at some point. I have highlighted the earth and neutral path in green. Before we make scope probe connections to the DUT, device under test, the common of the power supply is isolated from the neutral and earth grounds. So let's connect the scope via direct probe to the DUT output. Once that is done, the secondary side of the transformer is no longer isolated and the circuit's common is now at earth potential. Note that the scope is reading the correct plus 12 volts DC, and all is good with the world. What happens when we reverse the scope probe leads? We now have the earth grounding the positive side of the power supply, and we have set a new reference point, so the scope reads the correct minus 12 volts DC with respect to the alligator clip connection. As long as we only make one earth ground connection, or keep all the ground leads connected together and connected at one point in the DUT, all is still good. What if we want to test a DUT which doesn't provide galvanic isolation via a transformer? Here's a new DUT with no transformer. I got this circuit off the internet, and there are some component values for the DC power supply. When I drew the circuit, I just decided not to include any of the values because I feel this is a very unsafe circuit, and I never build one or want to promote one. So, just my opinion. Notice now that there is a direct connection of the neutral and earth grounds to the common ground of the power supply. As shown in the diagram, we now can make the test connections, and the scope's ground and power supply grounds are at the same potential or reference. So the scope reads the correct positive 165 volts DC. Reversing the probe connections, and oh boy, we've effectively shorted out the power supply through the grounding alligator clip via the common earth ground. At 165 volts, you would probably see a large spark that could pit the alligator clip, and I have seen that before. The DUT could be severely damaged, and with my luck, the fast-acting rectifier diode D1 would explode to protect the slow-responding fuse. Excessive current might damage the scope probe and open a trace in the scope, damaging it. So I marked a few problem areas in red. Another scenario, if you connect the scope probe's alligator clip to the common reference of the power supply, what would happen if the non-polarized AC plug was reversed? You would be connecting directly to the hot line voltage with an earth ground neutral connection. I wouldn't want to be there. Things like this can happen, especially when you have wall warts or brick double insulated power supplies and you've opened them up for testing. One fix is, of course, to use an external isolation transformer like the one found in the B&K Precision 1655A. With the isolation transformer connected, we are now back to the safer conditions shown in the first DUT example. If you didn't have an isolation transformer, another couple of options would be to use a dual trace oscilloscope in differential mode, which is shown in A, although there can be problems with that approach. B shows a differential probe set, and that can be an expensive purchase. And C shows a battery-powered scope, which can be very helpful provided you use a good quality and properly rated instrument. If you do not need the waveform analysis of an oscilloscope, how about a battery-powered multimeter? Since the meter usually does not have an earth ground probe, the measurements can easily be made, again provided that a properly rated instrument is used. As a bonus, the meter can have its probes lifted above the circuit's ground reference. In this slide, we see a device that has a metal chassis that is surrounded by an insulated enclosure or case, and regardless of which way the non-polarized plug is inserted into the socket, the unit would be pretty safe. Yeah, I promised to only use a few more Tiger reference. I'm definitely getting carried away. However, if the insulated case is removed for troubleshooting or testing, there might be a serious risk in working on the unit. Here you can see that the metal chassis is at earth ground potential, and the tester is also at the same potential, so the chassis is not hot. If, on the other hand, the plug is reversed, then the chassis is now hot at the line potential voltage of 120 volts AC, and a serious danger exists. Again, as shown earlier, using the isolation transformer would remove this hot chassis problem. There are some power supply designs that would have this hot chassis even if two-prong polarized plugs were used. So no matter what you are testing, caution is the operative word. Now let's go ahead and return back to the B&K Precision 1655A. Let's take a look inside the B&K AC power supply. By the way, it's manufactured in Taiwan. I have a few pictures I've taken here. Here's a side view, and you can see the major components are not really cramped in there with plenty of ventilation. If you remember, the sides were perforated. Also, there are two upper chassis support rails, which I think are nice, and so the case is fairly robust. I didn't notice, again, it's made out of steel, didn't really see any rust anywhere. This is a top view of the unit. The AC input, isolation transformer, the auto transformer, and finally the meter and the metering circuitry. The AC input area has a circuit breaker. The chassis grounds there, I did check it. It's got a lock washer on, everything looks good. And the transformer fuse and all connections seem to be nicely covered. Also, most of the hardware has the green Loctite type material on it from working loose. The isolation transformer is quite large and has dual windings on both the primary, that you can see on the left-hand side, the black and white wires, and the secondary, over on the right-hand side, the red and blue wires. For this 120-volt unit, the primary windings are in parallel, as are the dual secondary windings. But I don't see how in the field you could convert the unit, for example, to 240 volts, because almost everything else in the unit would need to be changed. A nice touch is that I noticed that they have the bolts both on the bottom and the side of the transformer that are to the chassis. And this should give it really good structural support. Again, this is the major weight of the unit, as well as help to maybe minimize transformer hum. Here's a close-up of the auto transformer. And again, there's lots of plastic boots and heat shrink for protection. Having said that, they are using exposed terminal strips in the other areas. And you also got a few free solder blobs stuck to the chassis, and you can see those with the little blue arrows I put in there. They're extremely small, and I really don't see how they'd be a problem in the circuit even if they broke free. But it would have been nice if they had brushed them out or used an arrows or something. The TO92 case, which is hard to see, is the Triac. And I was a bit surprised, even though it operates as a switch for great efficiency. I was expecting maybe a TO220 case. However, for me, I'm not going to be using the soldering iron feature. And also in the picture in the foreground, you can see the 3 calibration potentiometers that I found had a really nice range and were easy to adjust. And this is a final shot showing the PC board and metering area. A minor problem is that the black wire is touching one of the high wattage current sense resistors. Probably would not be a problem, but I will move it away from that component. But a complete fail is the so-called strain relief for the leakage probe wire. Even though I've seen this many times, I don't like the method of tying a knot in the wire. Even worse, the knot is in the wrong place, and before it does anything, the wire's solder connections are definitely being strained. It's easy to fix to move the knot closer to the front panel, and you don't have to unsolder the connection. But for me, I will be adding a proper strain relief. So in conclusion, on the pro side, the unit has good construction, components seem to be of good quality, and easy operation with a nice clean front panel. Calibration was also quite easy, provided you have the required loads. The range on the calibration potentiometers was very good. The unit offers a nice feature set with leakage testing. Overall, the manual is good with one major exception. Next slide. On the con side, the soldering iron controller is limited because there's no thermal feedback and no easy way to determine the temperature you're setting your iron to. Granted, only techs should be servicing this unit, but there are a lot of exposed AC line voltages inside the unit. Might be nice to have a push button to measure incoming line voltage levels. The unit has a very poor strain relief for the leakage probe, but that can easily be changed. And finally, there's no schematic diagram included with this unit. My understanding is that it is an option, and I guess you can purchase it. And sure, you could reverse engineer it, but it should be included. Yes, I'm talking to you, B&K Precision. I should mention I only checked the 3 amp rating for a few minutes and the 4 amp rating for a few seconds, and not at all the voltage levels. But overall, I really do like this unit, and I'm very glad that I have it on my bench. If you enjoyed this video, please give it a thumbs up and subscribe to my channel, and thanks for watching.